Hi, fam. Glad you could join us today. Yeah.
Yeah,
So
nice seeing you guys.
for sure. Yeah. So we really loved reading your work on DECO and how it laid the foundations for zkTLS as a really one of the most advanced technologies that we see today. So can you give us maybe first a high level overview of what DECO is trying to solve, and in particular, what kind of problem in the context of data provenance and access over TLS does it address, and how does it compare to kind of existing solutions?
Right. Yeah, so I think the capability enabled by DECO is best explained with an example.
Mhm.
So let's say Alice and Bob, they talk on the internet, and Bob is challenging Alice to prove, let's say she's over, 18, or she has like enough money in her bank account, or some facts about Alice. Alice could refer to some authoritative data source for to prove these claims. But the challenge is the internet we have today. The protocols running the internet does not sign over the data, so Alice cannot forward a piece of data from, say, the government website or her bank account webpage to Bob and convinced Bob of its integrity, because Alex could have generated the transcript or the screenshot by herself. And there's although the network traffic is cryptographically protected by TLS. TLS only encrypts the transaction, the transcript, but not doesn't sign over it. So the challenge is the provenance. You use the term provenance. It refers to the challenge of proving that the information, the data came from the correct source. And digital signature is a way to enforce provenance, but TLS does not sign data. So yeah, so there has been existing works on changing TLS or changing HTTPS to sign over data to sort of give you the direct provenance guarantee over the data. But those works face adoption barrier because it requires changing a piece of core protocols and potentially affect the millions of websites running out there. Um, yeah, so our goal with both Tangcry and DECO, we highlight the requirement of being legacy compatible. That's what makes this whole thing much more complicated, and that's truly, I think, the challenge. And if we don't care about being compatible with the reality, we could propose, changing TLS to sign the data, then we are, I think, technically we solve the problem. Yeah, so I think, yeah, so being compatible with the legacy system is where we differ from existing approach with in terms of both DECO and Tangcry. And there's, of course, the difference between the two is that Tangcry relies on trusted hardware. Back then it was Intel SGX, but DECO gets rid of that reliance, which is because primarily because TE has its own challenges in terms of side channels and so on. But I would say two designs, they do explore different trade-offs. They're not a replacement of each other. We can get into that later. Yeah,
Yeah.
but this is like the main distinguishing point is to be compatible with TLS. That's I feel that's why it's challenging.
Yeah, that makes sense. So can you walk us through some of like the high level cryptographic building blocks that DECO relies on to achieve its goals? Could you briefly walk us through, for example, how ZKPs are generally used and how that compares to just dumping everything into like a TE and calling it a day, essentially?
Right. So the core challenge of provenance in TLS, it sort of stems from the how TLS works. In
Mhm.
TLS, the user and the server, they negotiate a session key, a symmetric key, use that to encrypt and map the session. So because both the user, in our case, Alice, the prover, has the same information as the server, essentially. So a third party, Bob or the public, cannot differentiate Alice from the server after the fact. So the idea to circumvent the provenance problem is to limit the information available to Alice. So in DECO, we designed a protocol called the three-party handshake. So the idea is for Alice and the Alice here being the prover and the verifier, they both they run a two-party protocol to become the TLS user, the client, collectively, such that neither party has the entirety of the key. Therefore, Alice cannot forge a traffic that make it look like it's from the server. So, right. So then after Alice has done this three-party handshake and retrieved the data from the server, Alice sends over the retrieved data to the verifier. And at that point, the verifier can be confident that it must come from the server because Alice doesn't have the key to forge the transcript. So that's the MPC part. You mentioned ZKP part. So after this, we call this commit and approve. So Alice commit to the transcript. Then Bob has an anchor, and against which Alice can decrypt the traffic or selectively open part of it and approve facts about encrypted data, establishing the provenance then proof. So it's like the two-step process.
Cool. I'll pass it off to Yavor for some of the more technical architecture questions. Yeah.
Great. So you mentioned this three-party handshake. Can you go into greater detail about how this secret sharing mechanism in particular works in this context? And you mentioned that using this mechanism, no party has the complete picture for the data in order to be able to forge the session contents and etc. Can you elaborate on both of these things, or at least the architecture of like which multi-party computation protocol you leverage in this schema?
Right. So the TLS handshake, in general, at a very high level, it's a very complicated piece of protocol, but at a high level, it has two steps. First, you run the Diffie-Hellman key exchange. And second, you derive a bunch of keys from the key exchange protocol. The key exchange protocol gives you a secure, a fresh, maybe a group element. But you need a session key, which are the binary string. So you run it through a key derivation function to get the session keys. So the techniques to make these two steps, a three-party protocol is different. So Diffie-Hellman key exchange has nicer homomorphic property. We basically play a simple trick leveraging the algebraic property of Diffie-Hellman operation, so that when Alice sends over a public key to the server to do the Diffie-Hellman key exchange, Alice also incorporates entropy from Bob, from the verifier, so that Alice doesn't know really the private key to the public key, because the public key is a combination of Bob's and Alice's public key. So the Diffie-Hellman step is done sort of easier, sort of more algebraic fashion. And the key derivation process is less amenable to algebraic tricks because it involves running something through the hash function, which is very, it doesn't have, nice algebraic structure. So we had to resort to general purpose, like MPC. General purpose means you could run any computation in this two-party secure computation protocol. So at the high level, it's a way for two-party to compute, to evaluate the function over their private input, so that they learn the outcome of the evaluation, but not the inputs or anything else. Right. So they run this 2PC protocol, both providing their Diffie-Hellman intermediary results, and the outcome is a secret share of the session key. The MPC's computation is the key derivation function compatible with TLS, according to the TLS specification.
I see. Right. I see. So Moving to the actual, you briefly mentioned hash functions and other such things. This mechanism, from what we can tell, it supports both CBC, HMAC, and AES GCM cipher suites. What were the key challenges in adapting DECO to each of these suites, and how did your protocol design ensure selective opening was efficient in both cases? So effectively, how was your protocol adapted to these two different security paradigms?
Yeah, that's a good question. So DECO has two modes. We have a three-part handshake is one of the mode. The other mode is called the proxy mode. The idea there is that, well, remember the provenance challenge where the verifier doesn't know, where the data came from. The proxy mode is simply using the verifier as a proxy to see through, to basically proxy through all the traffic between Alice and the server. So that verifier has sort of a physical evidence that this byte came from the server. So the provenance is established through network, sort of network layer. The difference between CBC HMAC and the GCM is particularly like significant for the proxy mode because AES GCM does not have a property called it's not a commitment to the plaintext, so you could encrypt. So given given AES GCM ciphertext, which is what the verifier has, the prover could present a key that is not the actual encryption key and still decrypts the session correctly. So the prover doesn't have a lot of control over this, but it's feasible, right? You could commit to the session and decrypt it into different plaintext, which breaks the provenance, because ultimately we want the provenance for the plaintext. And so that basically says establishing provenance over the ciphertext alone is not enough because the plaintext could still be not committed to. So that is AES CBC HMAC has the commitment property, so it's nice that proxy simply just works. For AES GCM, it doesn't, so there's like additional complication in that case.
I see. Very cool, very cool. So now on a slightly more different topic, how does DECO enforce context integrity when the prover selectively reveals substrings from a TLS session? Could you explain how your two-stage parsing approach works and how it defends against attacks that exploit out-of-context disclosure? So you reveal something from the TLS connection that might have happened from a different session that would incorrectly give information to this third party of sorts. So how do you protect against such attacks?
Yeah, so I think that opens up a can of worms by its own, and there has been like follow-up works dedicated to addressing that problem. So at the high level, the concern is that since you can open just part of the response, you could literally like quote out of the context to the verifier. So the general idea there is that you need to reveal enough information to show that you're not like playing with the structure of you're not actively fooling the verifier by confusing the verifier of the structure of the response. So very concretely, if you don't open certain strings, for example, you need to then prove that those strings, for example, you want to redact, let's say you get a JSON response back, you want to redact a field. But one part of the solution is that you need to prove that whatever is not revealed, they are plain string. Let's say there's no like a quotation marks in the string, or other delineators that suggest that you are redacting over like two fields, hoping to create some sort of confusion about which field you are redacting. so dealing with this efficiently, it requires some careful thinking. And in DECO, we sort of made some simplification assumption that the original document has a structure, let's say HTML and JSON, they both have structure, and that you need to reveal enough information to show that the structure is intact, and only like the inner stuff of the structure is redacted. But as I said, there has been recent follow-up works sort of doing this so-called ZK parsing problem, and that has been I think, it involves reasoning about the grammar, context-free grammar parsing algorithm, etc. Doing that in ZK efficiently. I only know a sort of the superficial level of this line of work, actually.
No worries, that makes perfect sense. So, given that, so this is now this question's related to post-quantum cryptography and how quantum computers, since they're around the corner, it's good to protect against these things. We noticed that elliptic curve operations are fairly central to DECO's key exchange and handshake. We were wondering how tightly coupled DECO is with this current elliptic curve-based TLS infrastructure, and if it could be adapted to quantum-resistant schemes such as lattice-based cryptography or other such schemes. Like, in other words, how adaptable is this protocol to a post-quantum future, do you think?
Yeah, that's an excellent question. I actually I don't think we thought about that. This is a very good research question to think through. So I think very briefly, the protocol, I mean, the proxy mode probably is not going to be affected. But the three-party handshake, where the Diffie-Hellman, it's currently built around the Diffie-Hellman structure, as I said earlier, that part needs to be revamped. But that's an excellent research question to figure out. I don't have a simple answer for that.
I see, I see. So the protocol evolves efficient 2PC based constructions for query creation, such as 2PC HMAC. How would you reduce the overhead in this phase compared to using generic MPC protocols, since typically multi-party computation is a fairly expensive process? And which of the protocols ends up being the performance bottleneck in your evaluation? So is it the multi-party computation, the ZK part that is, like, which is the most time-consuming part of this schema, would you say?
Mm-hmm. So we played some tricks to reduce the MPC complexity, leveraging. So one example I can give you is when you evaluate the hash function in MPC. When we did that in DECO, we didn't need to go through the entire hash. So hash is like a chained function. We didn't need to. We observed that there's no need to evaluate all the steps. So we sort of jumped to the very last step, the step before the last step, and proved that the very last step is correct. And that turns out to be enough because it doesn't leak information. There's still one step of sort of hashing, and it's like collision resistant and so on. So that sort of observation can save a lot of cost in computing HMAC. Basically, instead of redoing the computation in MPC, you give the MPC the correct answer and you ask the MPC to verify its last step. So that's the high level idea. So yeah, well, the other question is what's the bottleneck? I think after our quite intensive optimization, the three-party handshake were actually quite efficient. I think so the challenge comes, the proof takes more time. The ZK part takes more time. It depends on how complex your protocol, the statement you want to prove. I think we had a demo where you prove you have I forgot what it involves, like two websites and proving that you have you're over 18 and you have an address in Cornell, like something like that. The proof generation was the bottleneck. But gladly for this application, usually the proof is like a one-time effort. You usually do it once to establish certain credential, then you don't need to repeat it very frequently.
I
That's
see.
yeah. I think in terms of bottleneck, it's the proof part.
I see, I see. So earlier, you mentioned that in prior systems, people have actually used TEs instead of using these zero knowledge proofs. Like I believe that it was called Town Crier that used this trusted execution environment. How does
Right.
DECO compare to this prior system? And I believe you alluded to there being differences in security properties and performance properties, but could you elaborate on what are the relative trust assumptions, security guarantees, and performance implications of using zero knowledge proofs and 2PC versus like Intel's SGX or other such trusted execution environments? Like, what are the more precise differences between these two mechanisms?
Right. So yeah, so the people being us, we also the time prior paper was it was like in published in 2016, um, several years before DECO. Um, I think the performance of TE. So at the high level, TE gives you this box in which you can run your program, and it proves the program run correctly and it produced a certain output. And it's a black box; nobody can see through the TE box and learn what's the secrets inside. So the Temporary protocol at a high level is to run the TLS client in the box so that the prover doesn't learn the session key. So again, the same idea. You want to limit the knowledge to the prover. But yeah, so the proof of both the provenance part and the proof part, the performance is basically there's little overhead over regular computation you have with CPU, whereas in MPC and the zero knowledge proof, I think I think on a ballpark there's like orders of magnitude overhead, right? Thousands of times, I don't know, maybe even more. But with TE, the overhead is quite small. It's measured in yeah, I think it's at least at most like certain, uh, certain 10%, 20%, something like that. It's not measured in the orders of magnitude. And the downside of TE is that if the TE actually has this, side channel vulnerabilities, a malicious prover could compromise the TE to learn the session secret, which breaks the provenance guarantee completely. So that is the downside. Assuming the prover can access this TE that produces the proof, and also being able to compromise.
Are the side channel attacks specific to the protocol that you're trying to run, or are they common with other T instantiations? Like, is it a particular like, is it in this particular case that side channel attacks are especially prevalent, or is it just a general vulnerability of the system?
It is a general vulnerability. Some side channel attacks can be mitigated by carefully writing your code in a constant time fashion. But some other attacks, they are more like on the CPU, like lower level, and they simply cannot be fixed by the application. I probably calling them side channel attacks is a bit narrow. Some of the vulnerabilities are like not side channel hardware vulnerabilities, let's say overall. Yeah, they are quite general, not specific to us.
I see, I see. So currently, DECO is designed to allow for one verifier in the free party handshake. Is there a path to extending DECO to support multiple verifiers or even public verifiability? In what scenarios, so for example, decentralized identity, voting, auditing, might this be a useful extension? So in other words, can there be more verifiers, and in what situations would you want more verifiers?
There certainly can be more verifiers. Simple way is to repeat DECO with multiple verifiers. Um, Or you can use, instead of two-party computation, you can use multi-party computation, which it also gives you four-party, five-party handshake, if you will. So yeah, I think it's in general useful in whenever you need to establish a strong proof of provenance. Because if it's only convinced a single verifier, you're literally trusting that verifier for not lying about what the verifier is convinced of. So here's a distinction actually. In some applications, the verifier is the one who consumes the proof. If I want to verify you are, over 18, I have like no reason to lie to myself. But there are other applications where the verifiers, others are consuming this claim made by the verifier. Let's say in this case of smart contract oracles, smart contracts are relying on a group of verifiers to make a collective claim about the DECO results. Yeah, so in those cases, being able to support multiple verifier, I think, is essential. There's different ways to do it with different, I guess, performance and the complexity, but it's having multiple verifiers are quite important if you want to, more public verifiability.
I see. So now, Jay, I think we'll do these last two questions about more general things about the ecosystem and how this can be deployed. So take it away.
Yeah, for sure. I'm really curious so our audience is like mostly like devs interested in the space and with some like technical background. So from the perspective of a developer interested in building on DECO, what does kind of the current tooling look like? What libraries or languages or frameworks should people use to integrate DECO into an application? And how should one go about implementing things around DECO?
So DECO has been licensed to Chainlink. I think their latest artifact is this so-called, let me send you a link, sandbox of DECO. My understanding is this basically gives you a way to play with it and design your query, I guess, through this web tool. Yeah, I would say for developers, this is like the current implementation, the entry point to DECO offered by Chainlink.
That's really cool. And how does the DECO tech stack relate to projects today that are building in the zkTLS space, say like Opacity or Reclaim? What do you see as kind of the most exciting future applications and directions for this technology?
So I think the zkTLS space is I think it's quite interesting, exciting space with there are companies doing more like the proxy mode. Also, there's implementations on the more like the three-party handshake mode. Also, I think that some companies are doing the TE mode, the town crier route as well. Yeah, I'm very glad to see different approaches are being explored. In terms of the exciting future applications, I think identity is something like very. I think it's going to be very like impactful because there has been a lot of use cases about attaching your credentials to basically to create what's called this decentralized identity. I was chatting with a researcher working on social media, decentralized social media. They are building a system for Blue Sky that allows you to attest that you're a researcher. So by connecting your org ID, this researcher identifier platform, by collecting your org ID profile to your Blue Sky handle, so that people know that you are a computer scientist or your opinions on computer science matters maybe can be more trustworthy, etc. So they don't. I think techniques like DECO and others, zkTLS can make that process more trustworthy. Their current approach is sort of there's a central like trusted guy who like do this connection, but this is one example of the identity verification. I think it goes beyond social network for sure. There has been like various other applications, even by government, or I think Google is rolling out their some zero knowledge based identity, systems. But yeah, overall, I think being able to use legacy data to enrich your online or decentralized identity is what I'm like. I think one of the most exciting applications.
Got it. Yeah. I mean, this is super exciting stuff. I think we're super excited about like the future of zkTLS and how DECO and its related applications will be implemented in this sort of world where, provenance identity are like pretty crucial in establishing what actually we see is like truthful in the digital world. So thank you, Fan, for joining us today. This was a wonderful chat to learn more about DECO, its applications, and its technical architecture. Yeah.
Of course.
Thank
Thanks
you.
for having me.